So all I wanted to talk about is like how much of a loser I've become since voice AI has like become a thing. So how much do you use voice AI?
Zero. I've never even heard of it.
Oh, as in like just you know how GPT has voice, so you can just talk to it.
Just generically,
Yeah, do you use it much?
not too much. I do use GPT-4 like every day, but mostly typing.
Okay. One of my team members brought it up, and I was like, "That's like I wouldn't use it. It's just easier to use like via typing and like coming up with a complex prompt." And then one day I gave it a chance while I was like walking because I was like getting a bit bored, and I wanted to riff on an idea that I had. And I was just like, "Oh, like I have this idea. Can you help me like bounce ideas back and forth with me?" And literally, I had like a 30-minute conversation with it, like explaining this thing back and forth. And I found the whole thing quite awesome. Like we came up with a board game, came up with the mechanics for the board game, how it work, all that kind of stuff. Then I made mine a dude. I think I forgot his name. Whatever it's called. He came up with like images for the civilizations in the board game, and I was like, this is so cool. So now it's my go-to. And in fact, before you called me this morning, I was talking to I'm gonna call him Trevor. I don't know who it is, but like I was talking to Trevor this morning. It was awesome. So good.
Wow,
Definitely worth a shot.
that's that's pretty interesting. I've only tried using GPT for like creative purposes once. Me and a friend of mine who've been like writing this fantasy universe together, and so we were like giving it all the prompts and everything and like snippets of text,
Wait, did you say fanfic?
fantasy.
Oh.
Just like like a Lord of the Rings type thing, but not Lord of the Rings.
Yeah,
No,
yeah.
you wouldn't catch me dead writing fanfic, AJ, unless it was fanfic of you.
You know, to be fair, that's how 50 Shades of Grey started. So, like, you know, might start with a fanfic and then, yeah. And also, if we get famous stuff, maybe people will start writing one about us, you know?
My AJ fanfic would be called back entry level for sure.
We're, you know what? Don't explain that. Let's just go on. Did you do anything interesting over the New Year's? Any like interesting goals that are, let's say, tech related? Any tech related goals this year?
Yeah, I mean, I've got a number of hats that I wear. So one of the companies, my goal is to get it to revenue positive this year, which is always a big milestone for any company. I think you spend the first few years burning through capital, and then eventually you hope to get profitable. So I think that's within reach this year.
I like revenue positive as opposed to profitable. It just sounds cooler. So, yeah, let's just use revenue positive from now
But
on.
revenue positive. Um, but I think it's very achievable. You know, we only need something like 40 paying users on the platform to make it happen because it's a fairly high margins platform. We've been able to use a ton of modern tech to leverage the hell out of this thing. So our operational costs are super low. And yeah, I think this is the year that it'll happen. We've been going through the sort of like these build phases and launch phases. So, you know, we've definitely been in that build phase for the last 2 years. This year is going to be launch phase. Hopefully, end of this year, next year is going to be like that growth phase. So, yeah, that was my primary goal, tech related. Other than get my podcast setup fixed. Does that count as tech related?
Yeah, it is. It is. I mean, it's IT related, which is close enough. Yeah, I wanted to I mean, as I told you, I want to learn how to code apps again. So I'm starting to learn Next.js and TypeScript and starting to build some stuff out, which has been interesting. I'm also trying to learn the meta learning process a little bit more. So I'm putting more emphasis on the process this time around, where I'm actually talking to various people, putting together a curriculum, understand the milestones I want to hit and how I approach it, and then reflecting back on the process. So I'm curious about this whole like, if I'm at level 2 and I have these skill sets and I want to get to level 9 with expanded skill set to achieve this project, what does that actually look like from a custom curriculum perspective? And I'm trying to avoid structured like courses. I just want to put together the critical pathway and only follow that.
You spent a whole week writing Python code, right? Was it last week, the week before? How'd that go?
Python. No, I didn't write Python. I wrote I mean I was playing with JavaScript, yeah. Went pretty well. I was building with Next.js, got like a functional thing out, and then realized how much simpler it is nowadays compared to like 6, 7 years ago when I was building on Node. You know, just like basic stuff, which I know will sound table stakes to you, but like understanding that I didn't have to build routes anymore and I just build a folder and put a file in the folder, I was like, oh, that's simpler. Like they've just abstracted so many things now. So it's become really interesting.
it's a catch-22 actually, because when you are like getting started, you have all this magic that's there that makes things just work, right? Like just putting files into folders and suddenly you've got routes. And depending on what you're doing, that's obvious or not obvious. But as you sort of like go further and further into understanding how these technologies work and how it's actually achieving all of these things, a lot of the modern magic is actually super painful. And there's this sort of like subculture that's growing within, um, I guess, technologists and programmers and stuff like that is trying to do like absolutely minimalist things. So like, just, the closest you can get to zero dependencies, the better, because there's less magic. And so when it comes time to pick this thing up and try to put it into a new context, you know exactly how it works, and you can, you know, fix it or improve it or modify it in the way that you need to modify it. Whereas when you've got this like 10 layers of magic built on top of 10 layers of magic, you spend actually more time trying to understand how it all works than with just building it yourself. When you eventually get to the projects that need that kind of flexibility, which is much later down the road these days, at least.
I think that brings us back to this whole like thing that you brought up. This was like months ago around like how important is the process versus the outcome, right? Because like if we don't know how things are happening on the back end, right? Like with AI, with abstracted code, whatever it may be, it is interesting. Like who's going to learn those things? It's like the abstraction away from mental math. Like I know a lot of people that can't do mental math these days because they just use a calculator, right? And so, um,
I can do basic mental math, but I command space has become my new mental math. I just do that and then I type whatever it is I need.
I didn't even know there was a thing. What does that do?
It just opens up Spotlight, but you can do maths with Spotlight. So it's like that's my mental maths. My browser app actually lets me do Control G, and I can just go straight into ChatGPT.
Oh, that's cool. Wait, is that already a thing? Like, is that pre-built or did you make that?
It's pre-built into Arc, which is the browser that I use.
Yeah, I started using Arc after you told me. It's so cool.
It's it's so I can't even describe what it is that makes it a better browser experience, which is the perfect UX, really. Like when you cannot describe why a UX is good, that's you've achieved peak UX.
This brings us to our sponsored segment of the podcast, not sponsored by Arc. But Arc, if you're interested, we love the product, so give us some money. We'll show you guys hard. But it's so sleek. It just makes me happy to work, to be honest, because it just like makes it. It's like when you have a clean desk, you just feel
Mm,
happier working, right? So
yeah.
anyway, we should get into today's topic, which is so we're playing another game because I like the deep tech Tinder thing. It seems like a lot of people enjoyed that, and so we're going to try replicating that this week. And so once again, we're diving into a field that we know nothing about. So first it was dating apps, and now we're going into gymnastics. Well, actually, you know a lot about gymnastics. Do you want to talk about that?
In another life, yeah, in another life, I was a competitive gymnast. Yeah, when I was a kid, I was training with the Australian Institute of Sport, and I was okay. I was sort of at the threshold where you cross into training for the Olympics. I bailed because I was already doing 16 hours a week, and like it just so many hours, and I was 15, and I wanted to go, play with computers and go to school and chase girls around, and I didn't want to spend half of my waking hours in the gym. So I never carried through, which I'm kind of glad for because none of the guys I knew at the time even ended up making it. Like getting into the Olympics as a gymnast in Australia is insanely hard. It's very, very challenging. Really, truly, only the best of the best because Australia doesn't actually have any guaranteed spots in the Olympics. You have to compete for them.
And you did
So
something easier, which was, biotech and coming up with different
so much easier.
systems. And,
Oh
yeah,
my
yeah.
goodness, yeah, yeah. I just fix other people's bodies instead of having to figure out how to use my own. Way easier.
See, you're being serious, but I think most people think you're being sarcastic. So I actually came up with a scoring system today, despite Long's background in gymnastics. So we're going to talk about 4 deep tech sectors that you may not think about. So we'll go over the details in it. It may be a company, it may just be a field. It's just things that we've been personally interested in that we're going to bring up. And then the scoring system is going to be between 3 different attributes from 0 to 10. So a score of 30 roughly. So the first one's going to be technical difficulty. So in a gymnastics routine, the difficulty of the routine gives you more points, I assume. So the difficulty of the technology, so 10 being the hardest possible thing, and 1 being the easiest possible thing, we're going to give a score from 1 to 10. And yes, you get a higher score if it's like more out there and like harder to achieve. Then the second one's going to be, so I know this, the metaphor is going to stretch a little bit. That's okay. Will they stick the landing? Which means, do we think it's possible? Like, will it be executable within like a reasonable time frame? 10 being, yes, we think it's possible in the near term. One being, this is probably so far off, it's like not going to happen in our lifetimes. And the third thing is just going to be cool factor. Like, how cool is it? How psyched are we about this technology? So those are the three factors. I know that's not how gymnastics works. Actually, I don't know. I have zero idea of how it works, but we're going to run with this metaphor because that's what we're doing in this show. We just butcher sectors that we know nothing about.
Fantastic.
So, would you like to be the first competitor?
Yeah, you know what? Why not? Okay, so I think we may have actually mentioned this in a previous pod, and it's definitely been in the news a bit. But when we first discussed doing this, the idea was to try and touch on things that maybe we think have flown under the radar. And this is one that I've been super interested by. So, sickle cell anemia is a rare disease. It affects about 100,000 people in the US. I think it's most prevalent in African Americans and Hispanics. So, it's a genetic disorder. And basically, what happens is there's this gene that is in part responsible for the shape of your red blood cells, or when it mutates in this particular disease, your red blood cell, which is typically this little disc, essentially gets turned into the shape of a sickle, which is why it's called sickle cell anemia. And ultimately, this kills you. And up until very recently, there have been no treatments for sickle cell. And recently, the FDA approved the first treatment for this, which is Casgevy.
So, just to clarify, it kills you because the surface area of the cell is decreased and therefore there's less oxygen transferring in, or is there a different reason?
I don't know what causes it, but it's a mutation in hemoglobin itself, and so it fails to deliver oxygen. But yeah, that's ultimately the issue. It causes like a restricted blood flow, and all of your tissues and organs essentially.
From memory, I think hemoglobin is special in the sense that once it binds to one oxygen, it like reorients itself so it can bind to another one quicker, and it becomes easier and easier. So I think it is to do with the surface area and like the ability for oxygen to bind to the hemoglobin. So if it's a sickle shape, I'm guessing it's harder for the oxygen to bind. And then you can correct us if we're wrong, but this is what I remember from like high school.
What's interesting about this is I'm not actually excited by it because it cures sickle cell anemia. Why I'm excited by it is that it's the first approved CRISPR-Cas9 gene editing therapy. So CRISPR made this big splash a few years ago. I think in 2020, Jennifer Doudna and Emmanuel Charpentier, I have no idea whether I'm butchering their names, won the Nobel Prize in Chemistry in 2020 for the discovery of CRISPR-Cas9, which is essentially a way of taking bacterial defense mechanisms against viruses and repurposing them as gene editing tools. So this is about as biotech gets. You know, this is this sort of crazy Gattaca future that you're imagining where you can go in and you can start gene editing people and, you know, and changing people's lives through those mechanisms. This was like all theory for many, many years. And then it became sort of reduced to practice and a series of patents were awarded left, right, and center. And there's been this whole series of patent wars around the underlying technology. But what's really cool about this drug is that it demonstrates that, you know, with an FDA approval now for the first time, that we can actually gene edit diseases away. It's always exciting when a new modality in the biotechnology or pharmaceutical field gets introduced and FDA approved, because it's sort of a demonstration that this technology is now capable of solving real diseases. And what's really, really fascinating about Casgevy is that because it's a genetic editing tool, you take this therapy once, then you're done. That's it, cured for life. And that's just really, really cool. So essentially how this works is they take your blood stem cells, they collect them, they use this CRISPR-Cas9 system to edit the related gene B something L1, I can't remember. And they essentially edit the mutation away, and then they re-inject these stem cells back into you. There's a round of chemotherapy, I believe, that is done in order to clear out other cells. And then they put these genetically modified stem cells back into you. They implant themselves into your bone marrow. They start replicating, doing what blood stem cells do. And then all of your red blood cells are now no longer have this mutation. And you're cured.
What's Cas9? What's Cas9 again? So,
Cas9 is the actual protein. So Cas9 is a nuclease, and what it does is how this system works is there's this thing called the gRNA, so guide RNA, and the way that this RNA works, RNA can attach itself to DNA. And so you basically look at your DNA, you come up with the resulting RNA, and you use that as your guide. And so this brings the whole molecule over to the area of the DNA that you want to modify. And the gRNA is just part of the bigger Cas9 CRISPR sort of system. And Cas9 is a nuclease, and what it does is it basically cuts DNA. And so this guide RNA brings it near the gene, and then Cas9 goes ahead and chops that thing up.
Cas9 is a defense mechanism against viruses, right?
Yeah, that's originally what it did in bacteria.
Okay, so typically a virus would come in, inject its RNA in, and then try to merge that with the current DNA of the cell, right? Well, that's one of the attack vectors. Is that correct? I mean,
I mean, different viruses work in different ways, but yeah.
yeah, and then Cas9 would come in and be like, "Oh, this is not meant to be here. Cut it out," and then moves it away. But we can program Cas9 to put in the DNA that we want, right?
Pretty much, yeah.
Okay.
So you can program Cas9 to cut specific areas of DNA that you've sort of designed it to cut. And so, you'd pick a site that's right next to the mutant gene in this case, and it would cut that out. You'd also give it a payload for the fixed gene, and then that gets edited back in.
So is the recent innovation that they made it work for sickle cell anemia?
It's FDA approved, which means it went through phase 1, phase 2, and phase 3 clinical trials and can now be used as actual treatment in humans at scale.
That's awesome.
Yeah, it's friggin' sick. I thought that gene therapy in humans as an approved therapy would take a lot longer than it did. These guys took a really smart approach of going after a rare disease, which is, I don't know what the right term is, not political reasons, but like the non-sciencey reasons, much easier to go after. You get accelerated approvals. You're dealing usually with a much more homogeneous patient population, so it's also sort of easier to construct your trials. I mean, especially if you're working with something like sickle cell where there are no other treatments.
Do you know how much about how you would program Cas9 to actually do what you want it to do?
I know very little about CRISPR-Cas9. I guess the most critical part, or one of the key critical parts, is the guide RNA. So every base pair in your DNA sequence, GTAC, gets transcribed into a corresponding RNA sequence, and they sort of have these counter pairs that bind really tightly. And so your gRNA, you can design it and put in sort of chemical modifications to make it recognize a DNA sequence quite strongly. And so you pick a DNA sequence around the one that you wanted to snip out so that Cas9 is able to orient itself on top of that gene. You do need to do it so that this thing called the PAM aligns. And that's sort of, it's like a sanity checker. So Cas9 has this guide RNA and then has this PAM sequence that says, yep, double checking that this is actually where I need to be cutting. And there's a whole series of innovations around CRISPR-Cas9 that people have started going for. So there's this whole like open source project where people are trying to create equivalents of the nuclease that are not covered by patent. And there are also people who are trying to make it way more specific. So the way that I understand the original CRISPR-Cas9 gene, like editing as opposed to just gene removal, was that you basically snip the DNA up and then you just chuck the new gene nearby and wait for the body's natural repair mechanisms to kind of fix it, which is obviously a bit of a shotgun-based approach. And so people are trying to create these like maybe more surgical style CRISPR-Cas9 systems or variations of. So it's still a very, very wide field of research.
If you're interested in this, leave us a comment, let us know, and we could probably do a whole episode on Cas9. I think there's so much to cover. I think CRISPR is pretty much like, from a computation perspective, like what, DOS, Windows 95, like there's a long way to go.
There's a huge way to go. Yeah. And there's a whole other, there are many, many other areas of gene editing as well that use completely alternative mechanisms. All right, so what's my scorecard for this? Give me my 0 to 10 technical difficulty.
Technical difficulty, I think, is probably like a 6. I don't think it's like that out of the realm of possible. I mean, the fact that we have it now working, probably minimum 5. Coolness factor, I love CRISPR. Like, I went on a deep dive many years ago, and that's why I was trying to pull back some of the memories of like me going through it and how it exactly worked. So I think coolness factor, definitely like an 8. And then, because I want room for improvement, if I give you a 10, I don't know what else you're going to pull out. And then stick the landing, I think this is a solid, like, I think this is a 10. Like, this is going to happen.
I guess it kind of has, right? I think I cheated that one. I picked something that's already FDA approved, which as far as a drug goes, is one of the big hurdles. I'm going to push back on my 6 for technical difficulty. I mean, developing a drug is notorious for being one of the hardest freaking things that you can do. An entire like gene editing in humans, 6. What's 10? What's 10, AJ?
you, you know the issue is we have two scores that like kind of almost like inversely correlated because if they're going to stick the landing, then technical difficulty has to be like kind of mid. But that's fair. You're right. It is quite difficult. But I'm saving like technical difficulties for things that like I'm not even sure is possible. Whereas like I think this is a matter of time, right?
Fair game. Fair game. I'll pay that.
Okay, I have something completely different for you, moving away from biology into space. So there's a company in Australia that does energy transmission. So they're called Aquila. Actually, one of the listeners requested that we dive into it. So I read the white paper, dived into a little bit more detail. There's not a lot in the actual construction of things, but there is like some pretty interesting things on how they're going to achieve it. So the base premise is that they want to use a bunch of mirrors in space to bounce energy, laser energy from, let's say, one country to another, right? So it's a transmission system for information and energy, starting off with energy. So I can dive into the tech, or do you have any questions specifically about the general concept of what they're trying to do?
Go straight. I mean, the concept sounds simple, right? But I have so many questions. But just start diving straight into the tech.
Okay. So there's a couple of different parts to it. First, they have to convert the energy into lasers, and the laser has to be in a very it has to be set up in a very special way to actually move the energy from the unit into space to the mirrors. And so you need it to be highly coherent. So it needs to be highly predictable and uniform as a laser beam. The cross-sectional area has to be optimized for space transmission, which you can use lenses and mirrors to do that. Basically, the reasons why you need to optimize it for it is because there's going to be all these different factors that you need to consider, like the distance that you transport it, the atmospheric effects that can impact the attenuation and various things of the laser beam. And it has to be low divergence. It can't spread out because things will have a tendency to spread out over time. And so you're programming all these different drivers to essentially figure out the conversions to make sure that it's being transmitted the right way. And then based on the atmospheric effects, you have to change the laser, right? Because if it's a rainy day, you have a slightly different laser versus like a sunny day and all these different things that could impact it. The other hard part is the lock-on system. So you actually have to lock on to the mirror before you beam it. Because if you beam a
Oh
high-powered
yeah.
laser back to Earth and you don't lock onto the right thing, then obviously there's going to be different things that could happen there. And then the last thing that's going to be really hard. So there's only two hard things. The lock-on system is really hard. The energy loss is actually going to be quite significant. So
That was my first question, is like, how do you even hope to begin to develop a laser that's efficient enough? Like the amount of energy going into power that laser versus the amount of energy you're going to extract from that laser on the other side.
basically I took the four sources of energy loss that I was looking at and then made GPT kind of come up with some sort of vague assumptions on like what that energy loss could be. Keep in mind this is like fully theoretical, like these numbers are like pulled out of nowhere. But the four main sources of energy loss is going to be quantum defect loss. So the actual conversion of like one wavelength to another wavelength of light in a medium, that's going to have some loss associated, right? So that's called quantum defect loss. Then you have atmospheric absorption and scattering. So the fact that you're passing lasers through a medium is there's going to be some sort of loss of energy. The divergence of the beam. So there's something called Gaussian beams essentially. So the fact basically that just means that there's like exponential loss of intensity as you go towards the outer edges of the beam.
You're taking a cross section
Cross
of the
section,
beam.
yeah.
Right.
It gets less intense over the sectional area. So as you move towards the edges, you're going to have some divergence because of that, and there's going to be a decrease in. Sorry, there's going to be a divergence, and because of the Gaussian principle, there's going to be less intensity in the center, right? Because as the beam gets wider, the intensity at the middle is going to become lower. So there's going to be some loss due to that, right? And the last one is actually just like the efficiency of the photovoltaic panels. Like you need to convert it into energy. And so the rough, like super rough calculations, like if we do like 5 to 10% loss from quantum defect,
Surely you
10.
can calculate the exact loss that you're going to get from the quantum defect if you know the wavelength that you're converting between. And my question would be, why convert between the wavelengths at all?
So I think they're testing different wavelengths. So my estimation here is that like I'm just doing rough calculations because their white paper doesn't go into detail. Maybe we'll have them on the pod and actually go into a lot more detail on the wavelengths. They do specify two wavelengths that they've tried, but I'm just keeping it very light. So atmospheric absorption and scattering, let's say 10 to 30%. And then beam divergence, I think we can keep this fairly low, so 2 to 5%. And then receiver efficiency, so 40 to 70%, because that really depends on the solar panels you're using. So the total efficiency could be anywhere from 24 to 56%,
Yeah,
roughly.
I back in the envelope, I calculated 40 using my command spacebar.
Nice. So I think the efficiency is definitely going to be an issue. Like we need to get that. And then the lock-on system, I think they're still figuring out exactly how to do it. But I think realistically, you're going to use something like LiDAR to lock onto the system because GPS is not going to be accurate enough
Mm.
to focus a beam onto let's say what, a 50 centimeter, 1 meter panel, like mirror. It's not going to
I
be.
mean, does it have to be so small? I mean, okay, in the sky it's fine, but like on Earth, you can have a fairly large cache, can't you?
Yeah,
Or is
true,
there a reason
true.
why you couldn't have it?
No, you could have a bigger one, but I think like the question we got was like how like is it like does the white paper make sense and is this like feasible? I think the answer is yes, it is feasible. Like all these things could happen, but those are the two like concerns I have. It's just like optimizing that energy loss, which they think is going to decrease over time, which is true. It will probably get more efficient over time. And then the other one is like actually locking on, which is I think most of what their research is right now. So I get the investor updates, and it looks like a lot of what they're doing is actually trying to get that lock on system. So they're trying to lock onto a moving drone right now and beam
Yeah,
energy to it.
that's interesting. Yeah, I mean, I guess it makes sense because like if you have, if you're missing, you can almost think of that as energy loss, right? Like if you miss 50% of the time, you've got a 50% degradation in your energy efficiency. So I know nothing about energy transport and what kind of efficiency mechanisms one is typically trying to achieve and what's actually practical. Do you know what that number is? Like how high, like if you have a certain amount of energy in one location and you're transferring it to another location, what's like your efficiency per dollar that you need to be able to achieve for that to be meaningful?
I think that realistically you want to compare it to like deep sea cables, right? Like because that's where 99% of the information transfer happens right now.
Well, that's info transfer. So are they focused on info transfer or energy transfer?
Well, we're not doing energy transfer between countries in a meaningful way at this point, right? So like it's hard to make that estimation.
Huge disagree. Huge disagree. We transfer entire like cargo ships worth of fuel.
Oh,
That's energy
actually, yeah,
transfer.
you're right. You're right.
So that's what I'm saying. Like, how much energy does it cost you? Like, what's your energy efficiency of like LNG, right? And what's your dollar per unit of like what's your dollar per kilojoule that ultimately is getting delivered? Which I mean, basically, you can just look at it as like, what's the what are you paying essentially for your electricity at home when it's coming from LNG? I guess that's the all in. That's your all in total cost for the end consumer. I mean, you've got a lot of middlemen in the way that you could probably get rid of, but at the end of the day, let's say I put like one of these caches on my roof, and they just beam laser energy straight to my house. Like direct to consumer laser energy. In which case, how many dollars do they have to spend to get a kilojoule to me? And how, like, practically speaking, how far away are they from that being, within a stone's throw of competitive?
That's a good point. I don't know exactly what that's going to be. Maybe we can do a little bit more research and come back to that. But I think in terms of use cases, there are also use cases that like aren't feasible with current tech that we have that we need this for. For example, like solar sails, right? Like for space travel, like this
Mhm.
becomes really feasible because you can beam energy to this thing and like do space travel that way. You can also have electric vehicles that just like don't ever have to go get charged because they just get constantly charged by like a mirror in the sky. So there's some interesting things that you could do there. Like especially sea travel, I think that could be interesting because they don't need to dock anywhere. They just get constant electrical energy beamed to them.
So, but what are the dangers associated with this? How bad is it to get hit by one of these lasers?
Probably pretty bad because you would need a lot of energy. So I think there is probably some issues around it. Considering that there's like these would be invisible, right? Like you could just walk into one and just get beamed because like contrary to popular belief, lasers aren't visible. Like they're not like lightsabers, right?
Well, the better the laser, yeah, the better the laser, right? The less you can see it, because the whole point is that you're trying to get as much of the light from one source to another, and
Exactly.
seeing something is light reaching your eye, which means the laser is not going where it's meant to go.
Yeah, or hitting some particulates and like just bouncing off, and then you
Yeah.
see that, right? So,
So do you know what laser actually, where that word comes from?
uh, no,
It's actually not a word. It's an acronym. So it stands for light amplification by stimulated emission of radiation. That's my little
I totally knew that.
etymology fun fact for you.
Yeah, yeah,
Yeah, I
yeah,
know. Every time I look up this fact, I'm like, I remember that. I now just remember the fact that it's not actually a word; it's an acronym. So technically, it should be spelled all caps.
fair, fair. Actually, that's a really good point. I didn't even think about that, but that's actually really cool. I like that. Any other thoughts on beaming energy from place to place?
I mean, there are obviously pretty sick military applications. I think there are applications for, you can measure dollar per kilojoule delivered compared to like modern energy infrastructure. But I think the more interesting use case is what you pointed out, which is like, how do you deliver energy to places that we just currently cannot deliver energy to? I don't know how much that matters in deep rural areas, or especially in sort of like highly logistically complicated military situations. But solar sails is an obvious one, beaming energy up into outer space. Um,
I think we're missing the most important use case here, which is that we can build an Iron Man suit now because you don't need a power source. You can just beam the energy to you constantly and just fly around the world. So now we're getting somewhere, and I think
You're right. I can see your Iron Man helmet hanging out in the background, just waiting for the rest of the laser powered suit to join.
okay, what's my score?
I'm going to start with coolness factor. It's pretty cool. Like anything involving lasers, I think is pretty cool. I think we jokingly mentioned lasers in our opening intro to this pod, so I'll have to give it. I'll have to give it a 9. I think for coolness factor. I don't know what it's missing, but I think there's just one. There's one buzzword missing there. You did throw in quantum, which is I always love to hear.
I know
Um,
you're scoring the idea, but for some reason I'm getting really nervous about these scores. Like I feel personally invested in the score that you're giving me, even though it's got nothing to do with me.
yeah,
It's just me presenting an idea.
it's a direct reflection of my like judgment of your intelligence. So
That's fair.
the stick the landing. So this is how likely are they to stick the landing here? That's a hard one. I mean, I don't really know anything about this field. I know that energy transport is incredibly complex, but maybe this is one of those situations that just kind of shorts cuts a lot of those complexities. All of those things that you mentioned, like in terms of efficiency loss, obviously the quantum defect one you can't do anything about other than just finding a wavelength that kind of works. A lot of the other ones, I think you can sort of figure out a way to get around. Um, I mean, while I think targeting drones is incredibly like difficult. Like trying to snipe a drone out of the sky from a satellite in space is an incredibly difficult thing to do. I don't think it's impossible. I think the catch is going to be: is it possible in a way that doesn't run out of capital first when you're trying to build this thing, and does it ultimately end up being cost efficient?
I think
So
it's also like what's the most efficient way to do this in general, right? And like if someone comes up with a room temperature superconductor tomorrow, is that just going to be a way more efficient way to do it? Like we just have cables under the sea transporting energy.
it's ultimately competitive, right, with other energy technologies. But ignoring that, so because I stick the landing. Are we including competitive advantage things here, or just is the technology going to be made possible with a reasonable amount of
I
money?
think consider all the factors.
Oh, that's even worse. Then I don't know. I'll give it a 7. It sounds pretty hard. I'm going to give technical difficulty. I'm going to give it an 8 as well. I don't think it's impossible. I think with enough smart people, you can definitely get it done. I guess most of my confidence in that score itself is based on I don't actually know what the rest of the competitive market looks like. I don't know what other technology in this space is doing. But technical difficulty sounds freaking hard. Um,
Okay, I'll take that. That's a reasonable score. I feel reasonably intelligent after that.
I forgot what I gave you. I think it's like 8,
7
7,
and
and
like 9,
8.
right?
No, 8, 7, and 8.
You said 9 for cool factor. Jeez, all right.
Did I say 9 for cool factor? Oh, yeah, I did.
24. All
79.
right, I'll take that. It's not
Yes.
bad. It's a pass mark.
All
But
right.
I am Asian, so my parents will be disappointed. So I'm wrong with
Yeah,
that.
well, you're not proper Asian. Yeah. All right.
No, what do you mean no problem? Damn,
All right.
can't even fully be an Asian. All right, you know what? Give me your next one.
All right, Tiny Corp. I actually think this guy, the guy behind it, George Holtz, is a pretty interesting character. I really love the way he writes. It's super like casual. It sounds like you're just listening to a voiceover that he took randomly on his phone. So this is ultimately an AI play. I think it goes bigger than that and becomes. I mean, he talks about being a chip fab play, which I think is bigger than artificial intelligence. I mean, when I read his blog, there's so many ideas that I get around doing this for things that aren't artificial intelligence systems. But what I find interesting about it is this discussion about AI at the level that I think very few people are discussing it, which is where a lot of the value accrual is actually going to happen, which is in the developing of the software and the developing of the chips that people use to build AI. So when there's a gold rush, you should be out there selling pans, not trying to find gold. And so this is very much a build the tools, sell the tools type of play. So Tiny Corp as a company right now, what they do is they, and he describes this so simply, it's beautiful. He just says, we sell computer boxes for more than they cost us to make, which is about the simplest breakdown that you can make. They sell these things called the Tiny Box, and that's how they make revenue at the moment. I think they raised $5 million recently. But really what they're trying to do, and I guess I'll walk it through the way that he walks it through in his blog posts and some of the discussions he has about this, is that really you have two major GPU manufacturers. There's AMD and there's NVIDIA. And NVIDIA is the clear and far winner without a doubt. But it's not because the hardware is better. Actually, a lot of AMD hardware in terms of like dollar per horsepower, AMD hardware is better. Now, the reason why NVIDIA wins though is that the software is better, essentially. Right. So when you use NVIDIA hardware, there's a whole suite of CUDA toolkits and NVIDIA toolkits from, really low level drivers all the way to really, really high level software developing tools. And something that he doesn't talk about, which I have experienced myself working in sort of supercomputing, is that NVIDIA also has much broader programs, as in not programs as in technical programs, but programs as in like essentially sales strategy programs, right? Where they make hardware available for free to researchers, or they have these huge cloud systems, where they've got, just a massive cloud of a bunch of NVIDIA GPUs, and they can, trial them out to people and you can play around with them so that you don't have to, if you want to test out an NVIDIA GPU, you don't have to buy one. And if you want to test it out for a supercomputer, that's really important because you want to test out how they work when there's a set of like 64 of them together. You don't want to buy and configure that manually just to test whether that's a good idea. And so when you go around, I remember one of the years that I was at Supercomputing, which is this massive conference, I went to this NVIDIA booth and they were like, yeah, we have all these programs for researchers and hobbyists and blah, blah, blah. And you can sign up here, here, and here and experience NVIDIA for free, basically. And AMD was like, yeah, if you want, you can buy this $200,000 rack of AMD's chips and then test it out. And I'm like, what? I'm not going to spend $200,000 buying these things just to try them out. Anyway, so NVIDIA, really, really great commercial strategy. Inferior hardware. AMD, superior hardware, absolutely inferior software, absolutely inferior commercialization strategy. Now, to highlight exactly how bad this is, George talks about, the fact that within the AMD drivers, there's like kernel panics, which is sort of like way within the operating system, well outside the control of programmers and sort of your average user. It doesn't work out of the box on standard versions of Linux, which is sort of the operating system that all developers use. And the compiler itself doesn't even let you get maximum flops. So when you run benchmarks, in theory, your hardware has a certain number of flops that it can churn through, which is floating operations per second. We measure this because floating operations are typically what you want to do. That's your basic mathematical operation. And you want to get as close to that peak as possible. If you have 1 teraflop, you want to get that teraflop in sort of like your code. And their compiler for the CL peak benchmark, which is like designed to maximize flops in terms of the algorithm, it doesn't even hit max. That's how bad their compiler is. And real programs typically hitting around 25%, which is an accurate estimate, which is the one that he gives, in my experience.
Wait, 25% of the maximum?
Yeah. So most of your algorithms are not actually able to take advantage of 100% of the flops. So if you're theoretically stuck at 30, 40%, the last thing you want is your compiler being so bad that the translation of the algorithm to the hardware drops another 50% of your flops away. And so the whole play of TinyCorp is basically completely subverting AMD's software and building that stack up themselves. So the RDNA3 instruction set, which is the instruction set that these chips are built on, is apparently very well documented and widely available. And so he's building a series of AI framework tools that compile straight to that hardware. They just skip everything in between. They skip CUDA. Well, I mean, you don't have CUDA for AMD chips, but they skip ROCm, which is sort of shitty attempt at doing that for AMD. There's no HIP, there's no anything. So you just go straight to this underlying instruction set, and he's got this super simple programming language that's only got like 4 instructions, and it compiles straight to this thing. It's super efficient. And essentially, the idea is that once you achieve that, you can then eventually. The nice thing about artificial intelligence systems is that you have very, very predictable sets of instructions that you don't need to be Turing complete. You just need a very, very basic set of instructions to get these tensor calculations through. And essentially, you can just build chips that are directly related to that. And you ultimately become a chip fab company. And he says that the software is the hard part. Getting that software layer right, where you translate a conceptual algorithm to something in the hardware, appears to be what people struggle with. CUDA is not very good. It is way better than AMD, but it is still not very good, especially for AI systems, because you have this super complex Turing complete programming language to try and describe something that is not actually any of that. So you have a super simple concept, which is I want to multiply a bunch of tensors together. And then you make that more complicated by expressing it in this fully Turing complete language. And then you expect a compiler to go back to the super simple expression. And it doesn't do a very good job. The situation is even worse on AMD. So for some reason, people just haven't solved this problem. I mean, it doesn't seem like a very hard problem, which is kind of why it's interesting to me that someone's actually going and doing it now and just cutting all of that crap away. I've experienced firsthand the pain of using things like ROCm and using things like CUDA and wanting to leverage AMD more than NVIDIA hardware. So I found this a super interesting play. It sits right at that underlying level. Most consumers will never hear about this concept, but I think it'll get increasingly become more and more popular with developers where they'll be able to write their artificial intelligence systems using the TinyCorp toolset. They will get maximum speed out of their hardware. And then eventually, TinyCorp starts rolling its own hardware and becomes a chip manufacturing company.
Is there a side by side comparison for? I think you explained it, but like, is there a side by side comparison for, say, AMD with TinyGrad, AMD with ROCm, NVIDIA with CUDA? Like, what's like?
Yeah, there's this whole benchmark suite called the MLPerf benchmark, which we can go and take a look at. I don't know any of those numbers off the top of my head. What I would say is that this is still heavily in development. So it's definitely not at the case now where it's fair to start doing benchmarks. I think that comes later.
I love this for two reasons. One, the tech, like, it sounds awesome. It sounds like such an obvious opportunity to go after. And this is one of those things where it's not about product market fit risk or, compliance risk or anything like that. It's purely technical risk. And I love companies like that because if you solve the tech, then the PMF is like obvious. The second reason I love it is the website's cool. Like, it's one of those really minimalist websites.
To say it's minimalist is to like truly everyone should go look at TinyCorp. I think it's .org. It's just
TinyGrad.org.
like
Because
tinygrad.org
TinyGrad is the name of their framework, and then
software.
TinyCorp
Yeah,
is the company. Yeah.
yeah, and it's basically just text, just pure text.
But people try this and they don't pull it off well. But these guys have done it like well.
Yeah, I mean, I think this works when you're truly a backend technology that consumers are never going to see, and that the play, as you said, is so obvious. Like his website, not only is it super simple, but it barely says anything because you really don't need to say much, right? It's like GPU software is shit. We're going to make it less shit. Done.
Yeah, I think you can make minimalist websites work for other things as well, but it's just very hard to pull off. Anyway, back to the tech side of things. I think this makes sense. If I was to score this, I think from a technical perspective, well, from a will they stick the landing? I think this is a 10. Just from a commercial perspective, like I have been seriously thinking about hardware for AI and hardware in general, like as a potential thing to like explore myself and figure out like where the opportunities are. So I think this makes sense. From an execution perspective, I think it's also wait, I said execution already. Execution 10, they'll stick the landing. Is it cool? I think this is like an 8. Very cool. I like it. There's also personal bias there because I like this kind of stuff. And then from a technical difficulty perspective, I don't actually know. I don't want to give a low score because I could.
I don't think it's I. That's the brilliance of it. I don't think it's actually that hard.
Cool. All right. Well, then I'll give it a 5. Oh,
Yeah, that sounds totally fair. Yeah.
yeah. I just want to offend a bunch of software engineers because I don't understand how hard it is, and like just abstracting the way they work could be hard because like as a physics major I could be like, oh yeah, the laser side of things is really hard and the software side is easy, but I don't want to make that distinction. But if you're saying that, that's cool. We'll give it a 5.
I feel like
That's
it's
okay.
I feel like it's not difficult to do this. It's just a matter of effort.
Okay. So last one I've got for you. It's not a company. It's just like I ran into a rabbit hole on the weekend and I just didn't really realize how extensive or like how important deep sea cables were, which I kind of talked about with the Aquila thing. But when Aquila's white paper, they were talking about how deep sea cables is the current way that we sort of move information, and the future will be bouncing it off satellites. I was like, what is deep sea? Like, what's so important about this? But 97% of international traffic, and in some sources said 99% of international internet traffic goes through deep sea cables, right? And they're about 700k miles long, so 28 times the Earth's equator. I think it's longer now because that stat was from a while ago. And they're moving data at anywhere from 35 to 250 terabits per second. And the cables themselves are mostly just protection, like most of the layers. So they're like maybe what 10 centimeters, 8 centimeters thick. They're pretty big. Actually, bigger than that. It's like it's at 4 inches. So what is that? Yeah, 10 centimeters roughly.
Yeah, something. That seems really not thick. Like my hand span is 20 centimeters. Like half of that as like a cable that runs across the ocean at the bottom of the floor. That seems real like
The reason I say it's thick is because the actual optical fiber is like half, like 1 millimeter, 2 millimeters, like a couple of millimeters. They're really small.
wow.
So it's just like this really tiny thread and then like a huge chode covering it, right? Of just like metal or something like that.
How many of these chodes do you have to get together to like support, the Sydney to Singapore? Is it the Sydney to Singapore cable?
Well, I mean, it'd be one cable, right? To do that.
But as in like, but how many actual cables would be in that route
Or like how
in
many
any given?
fibers?
Yeah.
So each of the like the fiber itself will have anywhere from 1 to 16 cores. I think 16 is probably the biggest right now. So a core, for context, there's this concept called total internal reflection where light bounces inside of a core, right? And there's if you position the light in the right way, instead of refracting out, it will like reflect in and just keep bouncing back and forth. And you can transmit data that way through a cable. So you would learn this in high school physics. Now, the way to scale this is you can modulate the waves and come up with different processes to transmit more data, or you just have multiple cores sitting right next to each other in the same cable. So the only reason you can't go to like 50 cores immediately is because there's actually cross contamination that can happen. They can interact with each other, and there's different effects that can happen. And also the manufacturing difficulties of shoving that many cores in a tiny wire can be quite tough as well. So I think 16.
But why can't you have like multiple, like, so you have 16 wrapped in a giant chode and then, or is it each chode has one core?
I think you can have multiple fibers, right? So if you have a core, like you have 16 cores in like one of those, I think it's a fiber or wire, you could have multiple wires, right? So you can scale it that way. But I think you still need to consider the interference that can happen between these things. So you have to be careful.
Mm.
And also every 50 miles, you have to boost the signal. So you have to convert it from light into electrical signal, amplify it, and then convert it back.
So I'm looking at this map of deep sea cables in Australia, right? Why do these cables, so there's a cable going from the east coast to the west coast and it goes through like the ocean. Why wouldn't you put that over land? Like, why don't we have giant land cables?
I didn't realize that. I'm looking at intercontinental cables. I didn't realize that we had a cable from east coast to west coast of Australia underwater.
Apparently, according to this map.
Interesting. I'm not sure. Maybe there's like less interference that could happen across the water because it's like so deep underground. Oh, by the way, the way that they lay these cables, if you're interested, they have these ships and they have two or three massive spools of like cables that just like sit horizontally, like winded this way. And then they have a sea plow. The sea plow will just like dig up the ground underneath as they drag it across, and they lay the cable right underneath. And Can you guess when the first cable was laid?
The 80s.
1842.
What?
So when they
Why?
wanted to do a telegraph from one side of New York Harbor to the other, they put a cable underneath. And then they did the first transatlantic cable in 1858 to again do telegraph messages.
Yeah, I totally forgot the telegraph was a thing. This gives me an idea. We should do like a rewind the clock. What was deep sec in the 1800s?
That's a great idea. We should definitely do that. Like we should dress up for it too.
Fuck yeah. I'll get my monocle, my top hat.
We're gonna talk like we're from the 1800s as well. I don't even know what accent that would
Oh,
be,
yeah.
but we can try. The only other thing I wanted to state was the fact that like the opportunities in the space. So obviously there's an opportunity to figure out faster transmission times because obviously the more we can transfer from country to country or continent to continent, the better. I think we're at 250 terabits per second. And the other opportunity, which I think is a bigger one, is that there's damages to the cables that happen, right? So you can damage the cable and an entire like I think there was a damage a couple of years ago that the entire west coast of Africa lost internet, right? Because they just got disconnected because one of the cables went down. So I think there is opportunity to look at protection for cables.
What is the average lifetime of a cable? Like just assuming general exposure damage.
25 years, but generally we swap them out faster because they become obsolete from a speed perspective.
Right. And how prone are they to natural disasters? Because when you're talking cross continental, like the continental plates shift, right? Like how does that matter? Are they flexible enough that that's not an issue? They get caught in earthquakes.
I mean, that's part of the planning. You have to plan to like avoid those sort of things. Have like what would you guess is like the most common mode of damage to a deep sea cable?
Uh, is it surprising? I was gonna say like
Uh,
fish, like sea creatures damaging it, but
yeah, not really. I mean, like I think the most common thing that people believe is that sharks. Yeah, well, it's actually human activity, which is fishing and
yeah,
anchorage is the two
yeah.
biggest sources. So 38% is fishing boats accidentally damaging the cables, and then 25% is anchorage. So they drop the anchor on the cable, which sounds so. I mean, surely like you would know because the cables aren't that big. You have a vast ocean to drop this anchor, and you just drop it on.
Yeah, it feels like of all the places that your anchor's gonna land.
Maybe because they're dragging the anchor as they go across.
That's why kind of why I guess fish trawling, right? Because you're dragging
Yeah.
these giant nets along the bottom of the ocean. So how does this? I mean, like when you talk about the opportunity here, like are you talking about things like Aquila, things like Starlink, like things that are fundamentally trying to replace these physical cables? Because I mean, that's the other one, right? It's like satellite-based internet.
Well, I was thinking just better ways to protect and bury the cables. Like those could be more immediate solutions, but yes, long-term solutions like maybe getting rid of cables altogether or figuring out different ways to transmit data and information that isn't so susceptible to damage. Essentially, like, like component failure is only 6% of the failures in general. It's usually humans screwing it up by some sort of activity, right? So maybe better detection systems for fishing boats and other things like that. And then I think what 14% is natural causes, so it's not that high either. So I think the immediate concern is how do you fix like people accidentally damaging these cables and knocking out the entire country
Mm.
from having internet.
It's pretty like I mean, I live in infrastructure. I've got a friend who's a massive infrastructure nerd, and we spent the weekend talking about tunnels. The okay, so what am I assessing? What am I giving you a scorecard on? Deep sea cables themselves, or like is that what I'm?
Yeah, I'm also sussing out the idea to the audience and you because I want to do an episode on deep sea cables and talk about like cable landing stations and
I would love to know how these work. So I would love to explore, like what actually goes into building one of these. What are the international treaties in place? Like, what's the underlying contract law that
oh, that's
governs
so
these things?
true.
Because
Yeah.
like that must be insanely complicated. Are they private? Are they public? They're probably some mix of both.
So the Fang companies, they have all laid their own cables down because they own most of the internet traffic, right? So like they
Yeah,
pay for these cables to put them down, which is also wild. So I don't know what that ownership looks like. Do they own the cables? Like,
yeah. Who pays for them? Like, what's the liability? Are they taxable? When the information gets through this cable to the node, what happens next? Like, how do you actually how does I would love to see a bit, the life of a bit from like my computer to your computer, which does have to cross a continent.
so I asked GPT to give me that because I was interested as well. I don't know how accurate it was, but basically you have a starting point. It gets like it goes to your local area network, it then goes to like a larger network node, then it goes to your domestic backbone of the country, and then it goes to regional network, and then it goes to a cable landing station, which is where like it goes to the transcontinental cables, and then it lands in the country you want, and then sort of does the exact same thing in reverse. But that felt a little bit too high level for me.
Yeah, it's just a bunch of words in an order. Yeah, I mean, it's worth taking a moment for how fucking cool it is that like the internet works. Especially when you start studying at any degree, you realize that this thing that you take for granted that literally, I mean, for what it's worth, it pretty much always works. Like it pretty much always works. And that is really fucking cool when you think about how tough it actually must have been to get all of that together. So coolness factor, I think it's right up there. I'm gonna give it a 9. I think it's equally cool compared to the Aquila concept to me. I guess stick the landing. I guess it's a 10 because it already is stuck. Like we've been doing this for 200 years apparently. So I don't think there's any argument that the internet works and that deep sea cables work. Technical difficulty, I don't know. Like I really have no benchmark on which to describe that one other than the fact that I mean if a whole bunch of private companies are doing this and we've been doing it for 200 years, surely we have kind of perfected the art and it's not particularly difficult and it's just a matter of which is why I'd be so interested in seeing the underlying contract law because that's probably the biggest thing. It's probably not technical difficulty, it's legal difficulty, it's liability offsetting. Like it's trying to figure out how does this all come together, like who's paying for what, how are they taxing it, how are they getting value back out of that, how is liability being distributed between the different parties, you know, what is the international law that covers these things, like if some random fishing ship damages this in the open ocean, is that actually like a crime, how well documented are the locations so that people can avoid them, and so I would say technical difficulty like a 3. Low technical difficulty. I think most of the complexity is going to come from actually doing the project's contracts to get this thing off the ground.
Okay, I'll take that. That's a fair score. If you want a full episode on deep sea cables, the technical side, the contracts, the law, everything goes into it, let us know because when I did research for this, all the videos and like stuff online is like 8 to 10 years old that explains how to do it. So like there wasn't really that many recent videos on it. And I think because like people take it for granted. Like I took it for granted. I didn't even know about this stuff until I started researching. And I was like, wow, these are cool. Like like you look at these maps and they look insane. If you just search transcontinental cable map or like deep sea cable maps, like you can just see this huge array of like vast networks going from country to country, which makes it feel like we've like it's like it almost looks like a virus, like we've just taken over this world. Like
I don't know. That analogy is such a lame analogy. So no, I will say that something that I do. The only reason I know about deep sea cables at all, I don't know how. Like I don't know that anything about them in great detail. All I know is approximately where they run from. Because when you're picking server locations, when you're trying to do like multi-location stuff, we consciously pick locations that are like right next to where the deep sea cable lines are. If we know that we have, you know, so for example, we have a major team in Singapore, we have and so obviously, if you're a team in Australia, you want your nodes to be in Sydney versus in Canberra or Melbourne because you have a cable that runs directly to Singapore from Sydney. And if you put one in Melbourne, then you'd have to get it from Melbourne to Sydney and then from Sydney to Singapore. So that's the only reason I know anything about deep sea cables.
that's pretty good. That's more than I knew before this weekend. So you should take that.
What that they exist and that they run from an approximate map in my head of where they run from.
I genuinely thought This is gonna be, it sounds sad to admit, but I genuinely thought there was more traffic going through satellites than there actually is. But it's only like 1%. I thought there was more information traveling that way than under deep sea cables. I didn't realize it was 97 to 99% that traveled that way.
Yeah, I think that'll change.
Yeah,
Like,
for sure. Yeah, it definitely will change. I think it was 100%, and then it's like slowly starting to move the other way. Okay, so there's two things I want to say before we wrap up. So first one is, if you enjoyed this style of episode, let us know. Let us know what you think. Give us a comment. You should be able to do the Q&A function in Spotify. There's various ways to get in touch. DM us on LinkedIn or Twitter and tell us what you think. If you like this style of episode, we can keep doing it. If there's a particular topic you want us to do a full episode on, definitely can. Just let us know. And the second thing is, if you're listening to this episode, you have taken the technocratic oath. So this podcast isn't free, unfortunately. It is paid for via subscribing, liking, following, and telling one friend about it. That's the only way you have to pay for it. So we spent a lot of time researching these companies, reading white papers, and putting together this content. So, what is it? We put in 5 hours, and Loong's time is worth like, I don't know, 20,000 an hour, and mine's like five. So like, that's
$5 or 5,000.
$5. We'll see. We'll see what people are willing to pay.
Uh,
And so, I think that's a good deal for you if you decide to just tell one friend about it. If you value your social capital under 100 grand, definitely a great deal. So make sure you tell people about it and keep listening. We'll see you in the next episode.